Okay, so what we're going to do next is talk a little bit about how these extended surfaces, they're sometimes called fins, right? So fins show up all everywhere in heat transfer all the time. So you have any kind of look at a computer chip, or you look at a heat exchanger, you kind of look any application, there's going to be these extended surfaces, which are called fins, that the purpose of them is to take heat from a surface and reject it to the surroundings, right? It's kind of the main point of heat transfer application, is to move heat from one place to the other. So you'll see fins show up all the time. It turns out that fins are usually described in terms of something called a fin efficiency. All right, and so we need to understand a little bit about fin efficiency, because you go look in your textbook, you're going to get an equation for fin efficiency. You need to know how to interpret that. Okay. All right. So let's see. So fin efficiency requires that we understand the heat flow into the fin relative to some kind of reference condition. All right, so let's start by figuring out what is the heat flow that's going into the fin. Okay. So first we look over on the left-hand side. So let's look here, right? I've told you TB. And I've heard this misconception a couple times now. So I told you TB. What do we know about the heat transfer there? Do we know anything about it? No, right? We don't know anything about the heat transfer. Just because I've told you TB does not mean we know anything about the heat transfer. It could be zero, it could be positive, it could be negative. TB is just a sort of a very local understanding of what's happening. But based on the gradients, we might have heat transfer in any way. So we need to actually evaluate the heat transfer using our temperature equation, but we have to use Fourier's law. So there's kind of two ways to do this. All right, so the first way is let's draw a control volume around this entire fin, like this. So my job now is I want to figure out what's the heat transfer from this fin, right? There's two ways. One is I could look at what's going in across this boundary here, right? This Q dot fin, we'll call it. Right, I could look at that and evaluate the conduction at that boundary, and then do the calculation. The other way is I could look at, I know the temperature profile is a function of position. So I could look at my convection, right? Q dot fin due to convection from the entire surface and do an integral. So let's write that out. So we could either do one of two things. We could say Q dot fin is equal to Q dot x, right, at x equals 0, which we would use K AC dt dx at x equals 0. Right? That's one evaluation we could do. The other thing would be we can say Q dot fin is also equal to Q dot convection, which is the integral from x equals 0 to L of h bar perimeter times t, right? T is a function of x. That's our function we just derived. T minus t infinity dx, right? Those are the two ways that we could evaluate this. For me, I think there's probably one way that's quite a bit easier. I guess you could certainly do the integral way, but the derivative is pretty straightforward, and it's really in line with the other things we're doing, evaluating Fourier's law. So let's do the calculation based on conduction and just kind of see how that pans out. Okay, so let's do that. We have Q dot fin was equal to minus K AC dt dx at x equals 0. So let's plug in, right? Here's our temperature. We have to plug in our temperature solution here and then evaluate that derivative. Okay, so that becomes minus K AC times d dx of our temperature solution. Our temperature solution was T infinity plus TB minus T infinity times cosh of mx. Okay, minus, all this goes inside here, minus TB minus T infinity tanh of ml times sinh of mx. Sinh of mx, okay? And all of that is evaluated at x equals 0, right? Sorry, kind of got crowded there. Okay, so that's our expressions. We just go through and evaluate it, right? We just evaluate this derivative. Okay, if we do that, we end up with q dot fin is equal to, let's see, minus KAC stays out front. Those are constants. We have TB minus T infinity. Okay, we pull that out of both of the terms. The T infinity went away, so we pulled that out, and we have now m sinh of what, m times 0, because we're evaluating x equals 0, minus tanh of ml times m times cosine or cosh of m0, m times 0. Okay, getting closer. Simplify this down, and we end up with q dot fin is equal to, let's see, we flip around, what do we do? So yeah, we flip some things around, we end up losing that minus sign, so it's just k AC TB minus T infinity tanh of ML times M, right? And again, remember M here was perimeter H bar over KAC, the square root of that. Okay, so we substitute M in, let's see, what are we doing here? So if I bring that in, I have KAC over here, and it ends up simplifying down to Q fin is equal to the square root KAC H bar perimeter, square root of all that, times TB minus T infinity times tanh of ML, tanh of ML. Okay. Hopefully we got through that okay. Right, okay, so here now is our expression for heat transfer into the fin. This is the total amount of heat that's being rejected by the fin, right? It's equivalent to doing the surface integral of convection loss, or just evaluating at the base of the fin, right? They're equivalent solutions. So here we have our q dot fin. So a couple of things to notice. This should kind of make sense. Okay, so tanh of ML, that's going to be a parameter that depends on our geometry. Right? It helps us scale. Heat transfer should be related to the difference between the base temperature and the surroundings temperature, right? That should make sense. And what else should we see? Well, if we increase conductivity, we increase the cross-sectional area, we increase the area and the convection coefficient. All those things should positively influence q dot fin, and they do, right? So this solution should make sense to us. Okay. All right, so let's now move on to how we actually are going to use this. Okay, so the point of this is, I told you before, we're trying to get to fin efficiency. Fin efficiency is useful, it's how it's typically reported. So we have now one heat transfer rate associated with the fin. The next thing is we need to find a heat transfer rate that represents like a baseline. Like what's, if we're talking about efficiency, it's heat transfer relative to what? What's our best case heat transfer that we're using as a baseline, right? So let's see, let's think to kind of think about this. Scroll down here. So let's look at this, this plot. I showed you this, beginning of lecture yesterday, or part of it I showed you. But this is now a plot that shows for this fin that we've been analyzing, the temperature as a function of position, or dimensionless temperature, that T minus T infinity over TB minus T infinity, as a function of dimensionless position, right? And this is for different values of ML. So thinking back to, let's scroll up a little bit, right? So thinking back to what ML is square root of perimeter H over KA times L, okay? So if we increase ML, what are we actually doing? We're either increasing the perimeter, we're increasing the heat transfer coefficient, or we're increasing the length. So we're effectively making the fin longer, right? We're making it harder to get heat from the base all the way out to the end of the fin. So for larger MLs, we should see that the temperature profile kind of drops more quickly, as a function of position. Right? And we see that here. We see for a really big ML, we're essentially talking about a fin that's really, really long, right, relative to some of the other thermal properties. So right away, you lose all that heat. If we have a really short fin or really low ML, it's saying it's really, really easy to move heat through in the x direction, which just becomes essentially a very short fin. Right, so what we want for our fin efficiency is to consider the limiting case where the fin is sort of infinitely short. Another way of thinking about this is Q dot fin when K goes to infinity, right? When the thermal conductivity goes to infinity. So which of these cases would that be? Well, it would be like this one here. If effectively have a very, very short fin. It's really, really easy to move heat through the entire fin. And that means basically I've got a temperature through the entire fin that's equal to the base temperature. Right, that's the limiting case that we're talking about. Okay, so writing out our fin efficiency, we write this eta fin. So eta fin is our fin efficiency. And it's going to be conceptually, it's just the heat transfer to the fin divided by the heat transfer, heat transfer as K goes to infinity. Right, and I picked K just because it's conceptually easy to think about, but really what we're saying is as ML goes to 0. So it could be K, you could have any of the other parameters playing into that too. Okay. Let's see, so let's write this out. So eta fin now, eta fin is going to be Q dot fin, that thing that we just computed before, our solution from above, up here, right, that guy, divided by what? So we need, what is the heat transfer as K goes to infinity? So it's going to be, we're talking about this fin has convection, so it's 8 bar times parameter of the fin, right, times L, right, that's the surface area available, times what here? So times the maximum possible temperature. So if the entire thing is at TB, now we just have TB minus T infinity. Right? So that's the maximum rate of heat transfer that you could get. So we would call this guy down here Q dot max. That's the maximum rate of heat transfer that you can get from this fin. All right, let's see. So let's put this stuff together. So let's actually take our solution that we had before, that Q dot fin minus the square root of the KAC, all that stuff. Let's actually substitute it in here and get kind of a compiled solution. So eta fin, bringing in our solution for Q fin, gives us the following. So it would be the square root of KAC times H bar times parameter times TB minus T infinity times tanh of ML, divided by H bar times parameter times L times TB minus T infinity, and that's our fin efficiency. Okay, a couple things to point out. Most important thing to point out, I guess. TB minus T infinity cancels out. Right, so fin efficiency, it turns out, doesn't care what the temperatures are. So you could have a really big temperature difference, you could have a really small temperature difference. The fin efficiency is only a function of the geometry of the fin. Right, the geometry and the heat transfer characteristics of the fin, and not a function of temperature. Right. So we can also, the other thing to point out is we can kind of simplify this a little bit. So we bring this, combine it with the square root, and we end up with an expression, eta fin is equal to, so tanh of ML, and this actually all simplifies down to just 1 over ML. Okay, so this is actually for this particular fin that we derived, adiabatic tip, Constant cross-sectional area. This is the fin efficiency that you can use to compute it.